Good morning. Welcome to Krishna's class. Spaces and then applying a debating process to get the result. Now, this is the general strategy then. And it's not altogether difficult to get such spaces. There are many, in fact. And we prove that, in fact, in this context, quite often the uh, continuous functions with compact support do play a very important role, especially while applying the or developing the theory for partial differential equations. Quite often you will have to work on LP spaces, or you will be searching for solutions in LP spaces, and often many of the estimates that you make are done first on a dense subspace which is rather smooth, so that uninhibited you can differentiate and so on, and then proceed to the limit if that subspace is dense in the whole space, so that you can extend the result to the whole space. Now, this is the general strategy that one adopts using this. Therefore, it is important to know whether some nice smooth spaces are dense in LP. Now, this is just a sample of such results. Okay, and we will once again work with, because you know that when we worked out the completeness, we did not bother about the 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 basic set on which the problem is set to be a topological space. But here you would need it because you are going to talk about continuous functions on X. Therefore, we will have to make such the relevant assumptions for that. Because in the general case, when we proved that LP is complete, okay, what we were doing is that all Cauchy sequences do converge in the space. So the process was, so we were working on this one. See, on LP X, we introduced a metric. Therefore, LP, irrespective of what the structure of X is, okay, so we didn't need a topology on X. Irrespective of that, this is a metric space. Therefore, on LPX, one can meaningfully consider limiting clauses. So the structure of X was immaterial. It is actually the structure that we have got on LP that was relevant in that case. If you want to talk about denseness of CCX, you are talking about continuous functions with compact support on X. Because in the previous result, all that we needed was X, then a sigma algebra and a measure. This we had, but it did not say that on X you have a topology, or you did not require the mention of any topology on space to talk about the completeness of LP. I hope you get my point. But now, since we are interested in looking at the continuous functions with compact support in LP spaces on X, or continuous functions with compact support on X, then we need to define continuity, you need a topology on X. That is why we have to put some additional structure on X other than this. So let us do that. So we assume this is the relevant part. X is a locally compact Hausdorff space. A locally compact Hausdorff space, and M a sigma algebra on X such that all Borel belong to or in other words, we want all Borel sets to be measurable. Okay, let mu be a measure. On X, that is the measurable space X. Okay. Now, quite often what we look at is the following. We take CCX, which makes sense. Because we can about the continuous functions. So what we are doing is we are taking all complex valued functions with compact support on X. that is CCX. Let lambda be a positive linear function on CCX. CCX is a linear space. Okay. Let M be the sigma algebra induced by on X. Then contains all borrowed. That is, all open sets of X are now measurable. This is essential to talk about continuity. Okay, because we are talking about a map from X to R or C. So you have a topology on R or C, the range space. You have a topology on you require a topology on the domain space. Then you can talk about open sets then you can talk about continuity of functions. Because what's a continuous function? Something which pulls back open sets from the range space to open sets in the domain space. Okay, so that's a property that continuous functions do have. So you see that clearly you need a topology to talk about open sets in the domain, and already you have on C a standard open sets. Okay, so that is taken care of. And since M contains all borrowed sets, you are also assured that all continuous functions are measurable functions. Measurable. So that you can talk about the integral of that. Okay. Now let the unique positive measure induced by lambda on induced by lambda on X. So we take mu as the measure. Thus we have x m mu, where m consists of, or m has all Borel sets as members in it. Now we will take example. The usual example that often occur in applications is the case where x is equal to rk and m the Lebesgue measurable functions the Lebesgue measurable sets and mu the Lebesgue measure. Now what we want to prove is this. Okay, so this is a typical example and we will be often considering spaces of functions defined on Rk. Okay, especially partial differential equations, etc. In the case of partial differential equation, you will be often considering the basic space as Rk, and then on that you will be talking about continuous differentiable functions, or we will be talking about functions having weak derivative and so on. So that's something which we shall not bother about at the moment. In fact, what we are doing is we are in a way preparing ground for work or for applications in such areas. Okay, so that's an example that we do. Now, what we want to prove is the following. Take all compact, all continuous functions, compact support on X. So all these terminologies make sense because we have already got a topology on X. Okay. And then we prove the following. So this is the main theorem. Infinity CCX Before we prove this theorem, we make some remark on this. This means elements of LPU approximated as closely as we please by continuous functions with compact set. This is of great advantage, because you see that because this function has compact support, we are assured that the integral makes sense. Okay? So it is in LP mu, and you are talking about continuous functions, and therefore there is some amount of smoothness that you already attribute to the functions. Now there are several results that you can look into, like CC infinity and so on. Such results are there, but we are not going into it. So we are just giving a flavor of a basic result in this direction. So this is an approximation here. This is an approximation. It says there exists an approximation of any function in LP by a sequence of by a convergent sequence of functions in CCX. The convergent sequence converges to the function that we have picked up. Okay. Now we shall give the proof of this. The proof is not difficult at all, because what one does is make use of a previous result. Previous result is that to take an element in LP, you approximate it, say a real positive function in LP. Let's take that. Finally, you will have to work with mod f to the power p. Okay. So you take a positive real or a positive function or a non-negative function on x, okay, which is in LP. It can be approximated by what? By what are called simple functions, with the property that the set on which these simple functions take the value 0, okay, or the set on which this function takes value different from 0 is a finite measure. Okay, so I will come to that. What exactly? So this is our strategy. So we take approximate, in the first stage approximation is negative, non-negative, simple functions with the property that with the property that the measure of the set of all x for which uh, not equal to is finite, is finite, and you might wonder, we are talking about complex valued functions and then now you are talking about an approximation. Yes. Okay. But how is that working? So what you need is, see, this is the point that you have to get. This is non-negative. This is non-negative and it can be approximated by such physics. Okay. This is greater than or equal to 0 and mod f is non-negative and can be approximated by Sx as properties mentioned above. Properties given above. So that is the first step. The second stage is to approximate in LP This is the second step. So these are the two stages. So let us execute this. Okay. So let yes designate complex measurable simple functions on X such that measure of So this is the set S that we consider. If S belongs to, it's a simple function. S belongs to S and epsilon positive, then there exists CCX such that GX equal to SX except at the discontinuities, except on a set of measures 0. Less than epsilon, and that is the supremum norm of S. Okay, to understand this, what you have is this. You see that S is essentially a simple function. What does it mean? It takes only finitely many values. Okay, and it's measurable. Therefore, the set on which it takes a constant value is always a measurable set. Okay, so that is the nature of the functions that we get. So we look at all complex valued measurable simple functions on X such that the measure of the set on which fx is not equal to 0. That means, see, it takes only finitely many values, and there is a set on which the function takes a value different from 0. We also assume that the measure of such a set is finite. Okay, or in short, what we are saying, you are approximating it by simple function. Such approximations do exist. I mean, this is what we have seen earlier. Okay, so what one gets here is the following. So if you take an S belonging to S, use the letter S here. So if S belongs to S and epsilon is positive, then there exists a G belonging to CCX such that Gx is equal to Sx except on a set of measure less than epsilon, and mod G is less than or equal to norm of S, norm infinity of S. What does it mean? This is essentially the essential supremum of S that you are talking about. Okay, so we are taking a function G, or there exists a function G. See, this amounts to doing the following. Let us look at an example. So suppose 0, 1 is the X that you have, and you have a function which takes finite values, and there are some places where it takes zero value. Now you see that what you are saying is that you modify it at these ends so that you get another function g which is continuous. Okay. So you replace this by continuous function here. Okay, so what we do is we are approximating. See, the places where you have discontinuity, okay, you are going to make it smooth, and that can be done by in such a way that the total measure of the sets on which this function is modified is now is a measure less than epsilon, and also such that mod g is always bound by the essential supremum of L. That's how you work it out. Okay. So such an approximation do exist. Hence, by Lucian's theorem, which we have proved earlier, norm of G minus S, the P norm of G minus S, let us examine this. Okay, so let us first take prove the Lucian's theorem. Let us recall the Lucian's theorem. The Lucian's theorem says that suppose f is a complex measurable on X with mu of A finite and f of x equal to 0, x does not belong to A, then where x is A, G belonging to. So it is the application of the Lucian's theorem that gives this result. Okay, such that measure of is less than. Moreover, we may such a way that supremum of effects. Now this can be done. You see that the function that you take from CCX or the function, suppose f is a complex measurable function on x is property, and this is the approximation that you get. Okay. So let us compute this one for a moment. The inequality that we just. So what we did was we approximated through the simple functions, and then that is the theorem that we have proved before. And then what this theorem says is that such functions can be approximated by uh, uh, by a function g belonging to CCX. Okay, so the steps are the following. Okay, so let us compute this computation. This is because only on A the function is not equal to 0. One by E d mu, and that is equal to twice, because you see that this is norm of S, because we are approximating from below. So this is approximated from here. To which is equal to twice so that is what we have worked out here. Let's solve this inequality. Okay. So what do we have? We have the following, that is so what we have is this. We are going to approximate LPX by CC. This is what you want to prove. Okay. So what one does is that the function in LPX is approximated by what you call the intermediary class of the intermediary sets. Okay. So LPX is approximated by what you call this intermediary set, namely S. Okay. And then S is approximated by okay, so that you have a sequence here which is dense in this, which converges to this. Okay, you have a, for any function here, or what you call given an epsilon, you can make approximate, or given an f here, you can choose an element here which is lying in the LP norm as closely as you want, less than epsilon by 2 say, and then such function can be further approximated by functions in CCX such that okay, right, because you are getting smoothness by this approximation, right? Okay, so that is the advantage. So you take an f here, f is approximated in the LP norm by S, and then S is approximated by G, again in LP norm by G belonging to okay. So you get this way. So you something like F so this is the type of approximation. Okay, right? So it is a two-stage process. You are working with first with, see, you have this LP, then this is LP, then you have what are called S, and then you can approximate each function with the CCX. Okay, so take here S, then approximate S by this is the process. Okay, so we have succeeded in approximating f by continuous functions with compact support. That's a big result. Okay, now we make some rules. So this essentially proves the density of CCX in L. It makes sense. It's particularly interesting to look at the the relation between LP RK and RK. So here you see that we were writing LP mu, but now in the case of RK we put X. Here we are taking X equal to RK, as we have mentioned earlier, instead of, and you are using Lebesgue measure. Therefore, LP mu that we are looking at is essentially, so we have identified this is the change that we have made in the notation in the case of R. So we take P and metric on because all these functions are LP functions. There is no problem over that because it lives in a compact set and the Lebesgue measure of a compact set is finite. So that is not there. That is no problem. BP RK. Now DP is a genuine metric. We make this statement because since G are continuous functions, F norm of F identically. Okay. This is because of the continuity. But in the LP spaces, you cannot say. Okay. That's why it's a genuine metric. Also, on CCRK, okay, essential supremum is the same as supremum. that is equal to, by definition, it is the essential supremum of okay, which is essentially equal to supremum of the reason is that you are taking continuous functions with compact support, so they are essentially bounded functions. There's no problem. Whereas this need not be a bounded function, or what you call take an LP function. It need not be a or L infinity function. It need not be a bounded function. Now for 1 less than or equal to 2 less than infinity, CC LPRK. LPRK is complete. This we have proved earlier, which implies that the completion of the completion of this. Therefore, you see that LPRK is essentially the completion of C. Now you know that you take a metric space for any metric space, there is a completion. This is a completion means there exists, it can be embedded in a complete metric space. Okay, that is YD can be embedded by tilde obtained through the limits of sequences Y. So you take Y, you know that it may not be complete. Now you adjoin the minimum required class of elements to it so that it becomes a complete space. Okay. So it can be embedded that. So you are just adjoining to it all the limits of Cauchy sequences. Now this is also unique in some sense. This is an abstract theorem. Unique in the sense that if you have any other completion of Y, then it is isomorphic to E. So all completions are isomorphic to one another. That's the problem. So there is only essentially a abstract, the one and only one completion, which is designated by Y. Okay, so what you have here is CCRK you take. So the place of Y is taken by CCRK and D is taken as the LP distance function, and then it is embedded in LP. Okay. Densely embedded. Yeah. That is the result that you have. Now we will continue with this discussion in our next lecture. So we conclude this at this stage. Therefore, what we have proved essentially is CCX is densely embedded in LP. For one less than or equal to P, less than infinity. It's not true when P is equal to. Okay, thank you very much.